Okay, this is a little video that I'm going to talk about our calculator quickly here. Make sure everybody knows how to put it in their calculator. The first one we graphed was the uninhibited growth of bacteria. So when you graph these, you have to make sure that you put in the proper window. Well, if you start with 1,000 grams and it's growing at 1%, it's not going to grow very fast. So how many hours do you want to look at it for? So I said, let's look at it for 100 hours. If you go by 100, then you probably need to go by 10. And let's see, if we got 1,000, how fast do you think it'll grow? Well, let's go 2,500 for the max amount, and we'll go by 250. So that's our graph. That's pretty slow growth, but you can tell that's exponential. On the uninhibited decay, it's going to be just the opposite. We're losing, and it was, I believe, negative 0.087x. And we don't want to zoom it. We want to go window. Now, how many hours do you think it's going to take for that radioactive iodine to decrease? Well, I don't know how many hours. Let's go 50. If we go by 50, then we need to divide 0 to 50, divided by 10. We want 10 points. So that'd be 5. And then now we only had 100 to begin with. So we want to start with 0. Let me go back to that here. We want to go to 0 to 100 by tens and hit graph. Let's see yeah, that looks about right, doesn't it? Nice little exponential graph, exponential decay. And that would be concave down, right? Because it's got negative slope and concave up, sorry, and it's getting less negative. So that's concave up there. Now, Newton's law of cooling problem had this K business, right? Well, I want to show you on your calculator how to record that, okay, on your calculator, so you don't have to memorize or type all those decimal points, how you can get an exact number. So when we found K, we put it into that formula. Look at your notes. And we took the natural log of 35 divided by 42, which is the natural log of 5/6, okay, and then divided by negative 10, and you get that number. Now, we are going to store that number in alpha K. Store is right here by the number 1. That number now is always K. So if we go to the actual question, it asks what will the temperature be after 30 minutes? Well, it was 70 plus 28 minus 70 times e to the negative k, which is alpha k, t, which is 30 minutes, times 30. So now this K is stored in there for you. You don't have to type that number in. And there you go, 45.7 degrees Fahrenheit. On the second part, how long will it take to get to 45 degrees? I believe we ended up with the natural log of 25 divided by 42, close parentheses, divided by, which should have been negative K. I think we had K, but it should be negative K, I believe. And we get 28.45 minutes. So that should save you a step. Now, the Challenger problem, I want to apologize. That equation is accurate. I must have typed it in my calculator wrong earlier, but that is accurate. That is the correct equation, and it predicts at what temperature how many O-rings will fail. So on the first one there, it's 100 degrees. So the formula is 6 divided by 1 plus e to the negative parentheses 5.085 minus 0.1156 times 100 power, close parentheses, close parentheses. Now, that is correct. So we got 0.009. And what that means is we have a 0.9% chance at 100 degree Fahrenheit that we'll have O-rings fail. They'll be, we don't have a very good chance. I shouldn't say it's a probability. It's, that's how many O-rings will fail. Not very many, right? None, for sure. Okay, but look what happens at 60 degrees. Okay. Almost 1, 0.81. That's kind of scary, isn't it? 60 degrees Fahrenheit, and we get 0.81 failures. Now remember, we had 23 flights earlier and none failed. Think about how lucky we were. And then finally, 30 degrees, but remember, it was colder than that the day of launch. If we change this 6 to a 3, look what happens. 5 O-rings. So it's pretty sad to think that they were almost assured that we're going to have an O-ring fail eventually. Now, it wants to know, on D it says graph the equation. We didn't do that because I wanted to do it on here. So we're going to go 6 divided by 1 plus e to the negative, parentheses, 5.085 minus 0.1156x, close parentheses, close parentheses. Now, your window again has to be, you have to know what to put on your window. Well, there's only 6 O-rings, so we could go, let's see, that's Y, or that's temperature. So let's go 0 to 100 degrees by tens. We only have 6 O-rings, so let's go 0 to 6 by ones, and look at this graph. This is called a logistic function. And you can see that the lower the temperature, the more O-rings are going to fail. The more likely we're going to have O-rings fail. This was 100 degrees here. This is 90, 80, 70, 60, 50, 40, 30. Okay, so you can see that that isn't good. Now it says graph the equation. What temperature is the predicted number of eroded or leaky O-rings at 1? Well, this is what's cool. You can go here and hit 1 and graph it. So we can find that temperature simply by going second, calculate, intersect, 1, 2, hit enter one more time. 57.9 degrees. We would expect 1 O-ring to fail. What about 3 O-rings? Well, changes to a 3. Hit graph. And let's find that intersection. So I can calculate intersect. Yes, yes, yes. About 44 degrees. And then when would we expect to have 5 fail? Right there, and that would be, second calculate, intersect, 30 degrees. We would expect 5 to fail. Okay, so pretty tragic stuff there, isn't it? Now, the following data, the modeling part on the last one, and this is one that I am going to do when I get back to class with you, because we're going to do several. There's a whole section that I want to do on this. We're going to have kind of a wrap-up day, okay? So that last one, you don't have the data yet because I'm going to give that to you in person, okay? Have fun with it. It's a lot of neat stuff.